Today, we talk about statistical quality control, one of the most exciting topics that we'll discuss this semester. Kidding, it's not. It's probably one of the most boring topics that we'll discuss, but it's an important one. And I'll get into a little bit more of that as we go along, not just because of having the information and statistics to back up what you're trying to do or see what you need to do, but in my experience, so many people, managers, want to just come up with well, we think we should do it because we just think so. And people go with that. They're like, okay, well, you must be the expert in this, so we'll go with it. You bring in some sort of statistical control chart or some sort of statistical evidence, you'll look like a superstar, because people just don't do it. I don't know why. I always said if I was going to start a consulting business, I would just teach basic statistics because people don't know how to do it. You're going to forget how to do it. You're going to forget even the homework and all the stuff we do. You're going to forget it. But, go back and use some of that. I'm going to use some YouTube videos. Unfortunately, this is a little bit boring, and I'm going to kind of kill you with videos today because I feel like other people probably explain some of this a little better than I do. There's a guy that I use his videos. His name is, I believe it's Joshua Emanuel, and he kind of got me through my statistics in my doctorate program, just finding his videos and walking me through him and Norm Stone. Um, these videos of Norm Stone got me through it because I was completely lost. So, as you come up with situations and things, remember this, I guess, is the main thing I really want to get from all this. Remember to go back, find some statistical measures, put them in with the different things that you want to do. You're going to have proof of what you need to do. If you remember that, I like that statement Sean Payton made in that one RFID video we were watching, but he said, people say, well, it looks like, and he's like, no, it is, because they have the statistical information to go off of. And you want to be able to say that. So, just to lead into that, work real hard, drink some coffee. This isn't the most exciting, riveting hour and 15 minutes you're going to have in your life, but it's important. So, here we go. Uh, we're just going to describe the different categories. Statistical quality control. I mean, it's not rocket science. It's just using a set of statistics, information, however you want to put it together to evaluate. Um, this talks about quality, but really it can be used for anything, um, just about anything. So just using numbers and statistics to be able to do that. Let me peer it in here. Um, which reminds me, before I go any further, the career fair is Thursday. So make sure you sign up to go to that. Even if you have a job and you like your fellow students, you should go because if they don't get a lot of foot traffic, a lot of these companies won't come back. And there's a lot this time. It's the most we've had in a long time. So I would encourage you to go to the career fair, even if you have a job lined up. Okay. So just throwing in my 2 cents on that real quick. Different statistics. You've got descriptive statistics. So mean, standard deviation, those types of things. It's going to describe something. You've got statistical process control, which is pulling from different data that you will get. It might be from samples and different ways that you get it, but you're going to use that to decide, does something fail or does it pass? Is it going the way it's supposed to? And then accepted sampling, which is usually random from a batch of goods, particularly in manufacturing. They'll produce a batch of goods, they'll test a few of them, make sure they're good, and then say, all right, they're all right, we're going to keep moving on. So, or you might reject them from time to time. Different causes, common or random. Sometimes they're just problems that you just can't figure out exactly what happened. Um, probably never get to a point where we can identify everything. Uh, but the whole idea, particularly towards the end, we're going to talk a little bit about Six Sigma. really pushing towards trying to identify everything that you can. You don't want to have that mindset of we just can't solve it all, so we're just going to do what we can. You just want to keep pushing, keep finding different things. And then you have the assignable. You look at the errors and you go, okay, well, that was probably because this person wasn't trained, or this machine wasn't taken care of, or uh, improper forecast, whatever it might be. But something you're able to look at and go, okay, well, that's what caused it. We know that. Using descriptive statistics. So mean, range, standard deviation, all that stuff that you're probably familiar with. Everybody should have had QBA or at least be taking it this semester. Um, you get into these formulas and things, and to me, what this really is some math person who wants to confuse you and make themselves look real smart. I mean, look at that. I mean, come on. The mean, we all know the mean is like the average. Do you really need all of this to tell you the mean? So, um, mean, don't let this overwhelm you. Range and standard deviation, they throw again all these complicated looking formulas. And we're going to do your homework, you're really going to do in Excel. If I can't get to an example that I'm going to work through, I'll record one and post it for you to see, where I work problems that are almost exactly like the homework. So it'll kind of walk you through how to do it. Um, some of these videos we watch, hopefully it'll help anyway, but I'll do that just to make sure. Because it's not an attempt to get you overwhelmed and trying to figure something out. I just want you to get a little practice in it and see how you can be useful later. Distribution. So your normal distribution, this is, I think they'll talk about this a little bit more. This is like a soda bottling company, and they're saying it should be 16 ounces. So a small standard deviation, your curve's kind of tight. Larger standard deviation, it's a little bit wider. Depending on what type of product you're producing, depends on which one might be acceptable or what type of goals you have in your organization. Then you have the symmetrical, which is really centered around this point that you're trying to achieve, the 16 ounces. And then on this one, you've got your skewed distribution, which, at this point might be one of those times you can look at that and go, okay, what's the problem? We're putting too much in these sodas. You might have some ideas already about what the problem is. So using these different curves to try to figure out exactly where you're going. Control charts. Control charts have a center line, upper and lower control limit. I hardly ever saw these used, but they are good to have again. Just because you take this control chart, got your upper control limit, your lower control limit, and you look at these points, and as long as they're in here, I shouldn't say as long, I mean, there's other factors, but as a quick glance, you look at this and go, okay, it looks like it's in control, but then there's this observation that's out there. So that makes you go, okay, we might have a problem. Do you have a problem for sure? Yeah. Just with this, you don't know, but at least it's something to trigger you to say, okay, something's outside the norm. We need to look into this and figure out what it is. So hopefully what you're able to do is all of these factors in here between the upper and lower control limit are things that are assignable problems that you kind of know and can identify and fix. Some normal causes also. So just using those, you'll be able to figure it out. This video just talks about control charts in general. Again, I'm sorry for the lack of excitement in these videos, but again, I think these people probably do better than I do, and very important. So let's watch this one.
This is Jay Arthur.
Maybe.
People often ask me, This is Jay Arthur. People often ask me, what is a
It's weird. It doesn't want to play. Back it up. Go back in. Try again.
This is Jay Arthur. People often ask me,
Well,
what is a control chart?
this
What does it
video,
do for me? Why do I need
hopefully
one?
other ones will play because they're
Can't
going
I
to be
just
more
draw a
specific
plain
here.
old
I'm
bar
going
chart or
to
something like that?
more of an
And the answer is
overview
a
of the
control
control
chart will
charts and
help
looking at
you
them and how they
find a
work
lot of
together.
things
We'll
that are
talk a
going on in
little
your
bit more as
process
we
that you
go
wouldn't be
through
able
how
to
you don't
see
really want to
otherwise.
take
There's
one
literally
control
no
chart and
way
then
to
make your
progress
decision
from
off of that
3
one
sigma
control
in the
chart. You
Six
want
Sigma
to
world
use
to 4
others
sigma,
to
5
kind of
sigma,
verify
6
what's
sigma.
happening and what's going on. Setting control limits. So here you're using standard deviations. Um, most of the time, you're going to see organizations that will do a standard deviation. This 99.74 is usually something they like to use. It's pretty standard. So what they want is almost all of their products, whatever they're testing, to fall inside this range, or we'll use this one. And then your error rate is outside on either end, plus or minus. This may be perfect for you. So um, that's a standard that most people use. Sometimes they'll modify it a little bit, but usually 3 sigmas. Now, it might not be as important if you're producing something you're not as concerned about your quality on. So if you look at this one, 95% might be close enough. If you're producing, bottle rockets, if 1 out of 20 doesn't work, oh well, you're not really concerned about that. So using these standard deviation charts, you can kind of see where people like for their problems to fall. On your control charts, as you look at a variable, so we'll look at part that will look at some factor in there, whether it's height, weight, size, dimensions, volume, whatever it might be. It's X bar and R bar charts are usually used for that. The one that deals more with an attribute or some discrete value are P charts and C charts. Um, so we'll go in first looking at the X bar and R bar charts. Monitoring changes are generally what the X bar is used for. R charts are dispersion or the range. So when you look at the X bar, it could have some different variations for different reasons. And R bar, that range, how far is the spread in each of these errors? Looking for central tendencies. Again, you want to use these two together specifically, and we'll look at those a little bit more on why we should. So this one is going to go over.
Welcome to this statistical process control tutorial on control chart for X bar. We will be constructing.
I have too much open. I'm going to try to open it again.
This is Jay Arthur. People often ask me, what is a control?
Welcome to this statistical process control tutorial on control chart for X bar. We will be constructing an X bar chart from process data and then determine if the process is in statistical control. If you've seen
Yep, that was it. I think. I'm going to go ahead and back up and start this one over because you will do an X bar chart. We'll just skip that first video. You can go back and watch it if you want to, but you will do one of these.
first video in this series on R chart, you know that a control chart comprises of a center line, a lower control limit, and an upper control limit. Well, the center line for the X bar chart is X double bar, that is the mean of the sample means. Now, if the standard deviation of the process is known, this formula is used to calculate the control limits. However, we will be using the range in this video. In our case, the upper control limit UCL is X double bar plus A2R bar, and the lower control limit LCL is X double bar minus A2R bar. R bar is the average of the sample ranges, and A2 is found on the control chart factors table. We will be using this process data consisting of samples of size 5 collected every day for 10 days. Our objective is to determine if the process mean is in statistical control. As required in the control limit formulas, we will first obtain the sample ranges and means. The range is largest minus smallest. So for the first day or first sample, the range is 509 minus 496, which gives 13. We do the same for the rest of the samples. The mean for the first sample can also be obtained by adding up the values and dividing by 5, and that gives 502. We do the same for the rest of the samples. Next, we calculate R bar and X double bar. The sum of these ranges is 231, so R bar is 231 divided by 10, which gives 23.1. The sample means add up to 4,978, so their mean, X double bar, is 497.8. Looking again at the formulas for control limit here, we have everything but A2. To find A2, we simply go to the control limit factor table and check under sample size 5. The corresponding A2 value is 0.577. Now we have A2, X double bar, and R bar. So UCL equals 497.8 plus 0.577 times 23.1, which gives 511.1. And for LCL, we have 497.8 minus 0.577 times 23.1, which gives 484.5. For the chart, let's first draw the sample points for the data, and then draw the control limits, and finally draw out the run chart. The X bar chart is now complete. We can see that the sample mean for day 5 is clearly below the lower control limit. Therefore, the process mean is not in statistical control or is out of control. As a result, we recommend that the activities of day 5 be investigated to determine the special cause of variation and to take necessary corrective actions. And that's X bar chart. Thanks for watching.
I like to use this guy because I would play these videos and I would do a step and I'd stop it and go back and forth. So that might help you too. And he really walks through it really well. So, oops. I didn't realize I had the R bar chart right after it. It's very similar. A lot of the same ideas go along with the R bar chart, but remember that it is more about the dispersion and range in this process. So let's watch the one on the R bar chart.
How a process changes over time. They reveal the stability or variability in a process. They help us to distinguish between random and assignable variations. Random variations, also called natural variations, are present in every system. Assignable variations, on the other hand, are special causes of variation. So the objective of statistical process control is to identify and eliminate these external causes of variation. Here is an example of a control chart. It comprises of a lower control limit, LCL, center line, and an upper control limit UCL. If a process is operating within acceptable limits, we say that the process is in statistical control or stable. Otherwise, the process is out of control. For the purpose of this video, we will just say that a process is in control if, number one, there are no sample points outside the lower or upper control limits, and number two, the sample points appear randomly distributed. That is, there is no trend or other unusual behavior. Here is a control chart that shows the process is out of control because there is a point above the upper control limit. There's also one below the lower control limit. Either of these show us that the process is not in control. Here is another process out of control as there is a positive trend in the process values. This process here will also be considered out of control because of increasing variation between the values over time. In this SPC series, we will be discussing the R chart, the X bar chart, the P chart, and the C chart. The R and X bar charts are used to monitor quantitative variables, that is, variability and central tendency, while the P and C charts are used to monitor qualitative variables, that is, attributes or characteristics. In constructing a control chart for the range R, we will be using this process data consisting of weights of a snack pack specified as 500 grams. Samples of size 5 are collected every day for 10 days. Our objective is to determine if the process variability is in control. The R chart is used to monitor sample ranges, and it thus provides us with some information about the process variability. The range is the numerical difference between the largest and smallest value in a sample. Therefore, the range for the first sample is 509 minus 496, which gives 13. For the second sample, the range is 521 minus 492, which gives 29. Continuing in that fashion, we have the ranges for all samples. Next, we calculate the center line R bar, that is, the average of the ranges. The sum of the ranges is 231, therefore, the mean of the ranges R bar is 231 divided by 10, which gives 23.1. The formula for the lower control limit, LCL, is D3 R bar, and the formula for the upper control limit, UCL, is D4 R bar. D3 and D4 are obtained from the table of control limit constants. Here is the first 9 rows of the table. For ranges, we'll look to the right here for D3 and D4 values. Remember that the sample size is 5 per day. As you can see in this table, each sample has 5 values, while the number of samples is 10. Going back to the control limit table, sample size is 5, our D3 will be 0, and D4 2.114. So the lower control limit LCL will be 0 times 23.1, which is 0, and the upper control limit UCL will be 2.114 times 23.1, which gives 48.83. For the chart, we can first draw the control limits. Next, the sample ranges as points. And finally, we join the points with lines. The R chart is now complete. The sample points appear random, and there are no points beyond the lower and upper control limits. We can say that the process is within statistical control. If you plan drawing the control charts in Excel, I have posted a few useful links in the description below. Thanks for watching.
Okay, so R bar chart, very similar. Um, Similar process that we use, but the X and R bar charts, they need to work together, and this kind of tells you why. When we look at these, we can look at this X bar chart, and we see there is a point beyond the lower control limit, which means the process is out of control. If you had only had the R bar chart in this situation, you would think that your process was in control, but it really wasn't. On just the opposite on this one, you look at the X bar chart, everything looks like it falls within the correct range. And when you look at the R bar chart, this one is out of control, it's over. You also want to look at trends. So sometimes, just because you're within all these may not mean that you're in control. If you've got an upward trend or a downward trend, you might need to evaluate that and see why that's happening. Showed one where it was really tight around the center line and started expanding. That could mean it's out of control. So there are different factors and things to look at to know why that's done. Um, we're just going to roll through that because we're going to do all this in Excel, and maybe I'll get to it, but if I don't, I'll post a quick video. But you're going to put it together and put it in a chart that will be similar to this. So constructing, and this just goes into more of the R bar chart. The factors table, statistical factors table, it's something you can just Google. It'll come up. It doesn't change. They're all the same for those statistical factors table. Plus, I've got one clipped out on the example that I'll use to show you to go through there. Your R bar, of course, this one is in control. It's within the different control limits. So now we're going to move on to P and C charts. I know this is riveting for y'all, so just hang in there. It's important, good stuff. P charts, a lot of times are your yes and no decisions. They'll be used, this is talking about quality, but my brother who is in marketing for a pharmaceutical company said they use P charts and look at P values often to decide if they want to go to market with something. They'll do some research and come up with a value and say, okay, we're going to go or not go. And they'll use these numbers. The C charts are more when there could be different causes, different problems that they want to look at and figure out what types of things might have been the issue. If we look to the last class where we looked at the list where they were checking, I think those were genes, like one had a broken zipper, one had a hole somewhere, one was the wrong color, different things that there might be in the process. That might be it. It does look at the actual number of defects. So here is, this is going to be the P chart.
Otherwise known as the P chart. The P chart is used to monitor attributes and applies to categorical or qualitative variables. They're generally used to analyze the proportions of non-conforming or defective items in a process. The center line for the P chart is P bar, which is found by taking the total of defective or non-conforming items and dividing it by the total number of items sampled. The upper control limit UCL is P bar plus 3 times square root of P bar times Q bar divided by N bar. The lower control limit LCL is similar with a minus sign. Q bar is 1 minus P bar, that is proportion of non-defective items, and N bar is the average of the sample sizes. For our first example, we consider this process data consisting of the number of defective items in a sample of 200 items collected every day for 15 days. We want to calculate the control limit and determine if the process is a statistical control. The total number of defective items over the 15 days is 156, while the total number of items sampled is 200 times 15, which gives 3,000. We calculate P bar by dividing the total number of defective items by total sample size, and that gives 0.052. Consequently, Q bar is 1 minus 0.052, which gives 0.948. The average of the sample sizes N bar is 200, since every sample size is 200. Now that we have the 3 required values, we can now calculate UCL and LCL. So, plugging the values into the UCL formula, we have 0.099, and for LCL, we have 0.005. To ensure better accuracy, we want to take the square root immediately after evaluating these values. And also note that these 3 multiplies the result after taking the square root. Don't take it as a cube root. Now that we have the control limits, let us now calculate the proportions and construct the P chart.
The proportions are found by dividing the number of defectives by sample size. So for day 1, the proportion is 11 divided by 200, which gives 0.055. We do the same for other days, so we have all information required for the chart. And here is the P chart. Everything looks okay. No points beyond the control limits, and there is no unwanted pattern. We can say confidently that the process is in statistical control. Let's look at a second example where the sample sizes are not all the same. The sum of the non-conformers or defectives is 119, while the total sample size is 2249. That gives us an overall proportion or P bar of 0.053. That makes Q bar 0.947. The average sample size is total sample size divided by the number of samples, which gives 224.9. We now have the values required to calculate the limits. The upper control limit is 0.098 and the lower control limit is 0.008. Now that we have the control limits, we can go ahead and calculate the proportions. The proportion of non-conformers for day 1 is 10 divided by 224, which gives 0.045. We do the same for days 2 to 10. Now let's look at the P chart. You can see here that the proportion of defectives for day 9 is higher than the upper limit. Therefore, the process is out of control. We recommend checking for the cause of this unusually high value and addressing it. And that's P chart. Thank you.
All right, so good example of P charts. Go through and we'll look at these examples. It just shows, this is just talking about how to construct the center line again. It looks real confusing, but it's not as bad when you start doing it step by step. If you're like me, you kind of look at this and you go, holy cow, what is that, all that mess about? But, if I'll take it step by step, it's usually not so tough. This is an example of one, you're looking at the center line, your upper and lower control limits. One thing that's interesting about the P chart is a lot of times your lower control limit is 0. If you're looking at your yes and no's ideas, it either is or it isn't. So it's a little bit different. Now this is a C chart. This will be the last monotone stats video that we're going to go through this class. So let's watch this one on P charts. C charts, I'm sorry.
For example, the number of defective items per day produced on a production lot. The center line for the C chart is C bar, that is the average number of non-conformers over a period of time. The upper control limit is C bar plus 3 times square root of C bar, while the lower control limit is C bar minus 3 times square root of C bar. Now let us construct a C chart for this data. Here we have the number of non-conforming items collected per shift over 10 consecutive shifts. The total number of non-conformers is 86. So the average C bar is 86 divided by 10, which is 8.6. The upper control limit is 8.6 plus 3 times square root of 8.6, which gives 17.4. And the lower control limit gives negative 0.2. Since we don't expect negative number of non-conformers, we usually just replace negative lower limit values by 0. This applies to P charts as well. Now let's take a look at the C charts. We can see here that we have a positive trend. That is, the number of non-conformers is increasing on average over time. This suggests that the process performance is degrading over time. Therefore, the process is out of control and some corrective measures need to be taken. And that's C chart. Thanks for watching.
That one was pretty short. So Think about this one as number of errors. Some of the X bar, R bar, it might be more about being around that center line, but particularly in this chart, uh, as you get higher, you're getting closer to where you're having some problems, some bigger problems. I kind of went through all this, looking at the center line, how to calculate the upper and lower control limit. Went through that. So if we look at process capability and the index, so you really need to look at your process and think about what you're able to do. Just because you have a standard that you want to meet doesn't mean you can. Might not even mean that you should. That's probably more of a marketing thing, deciding if you should try to meet those standards. But you've got to know what you can do. If you need to invest more to be able to have better quality or not, or whatever it might be. But you've got to set your capacity and where you want to do it. Your process specifications might come in the form of your tolerances. How much is okay? This one in particular, bottle fill rate is supposed to be 16 ounces. As an organization, you decide, well, if it's plus or minus 0.2 ounces, that's close enough. It's going to be okay. The consumer's probably not going to notice it. Sometimes you pull up a bottle and you go, it looks like there's too much or too little, but 0.2 ounces, that might be the spot for this particular product. So when you look at this, you've got your limits set, and this is using this bell curve to look at it, but this one is meeting. This is what your specifications, what you want it to be. So 15.8, 16.2, you want it all to fall in there if possible. On this one, we can see that it has gone outside quite a bit. So if your information comes up and you process it and put it in this chart, you'll see it should tell you, okay, we're out of control. There's not filling enough and we're overfilling. Could be an issue. Particularly, if you're some big time, if you're Coke or somebody like that and it's skewed, you're filling most of them too much, you could be losing a lot of money because of the volume of product that you're doing. So you kind of look at that one to see what's going on. This one is very tight, right around this 16 ounces. So if you see this chart, do you think that's really good? Or does this process need some improvement? What do you think? A little tricky. Bit of a tricky question. Really good, or does it need some tweaking? Yes, if you're just looking at this quality number, that's excellent. Now, what you will have to consider, and this isn't with every company, but something you might think about or need to take in consideration, they might have chosen these limits because being able to speed up the process, but being a little less accurate, might in the end save money. So they might look at this and go, okay, we probably need to hurry up the process. Let's make our errors stretch out just a little bit more because we know we're going to make a better profit. So, that's one of the concepts behind it. Or they might go, hey, we instituted this process that we thought we were going to need plus or minus 0.2, but we're realizing that we can hit this mark, so they might change their standards. So the answer is yes and no. So it just depends on what your company's trying to do and what types of goals you're really trying to meet. Let's see, Six Sigma. Six Sigma has been around since the 80s. Motorola really started. It's really something that has taken hold. Many companies are trying to follow it. If not completely follow Six Sigma, they're at least taking pieces of it. So it'll be important that you understand Six Sigma. I don't know how many times in interviews and different things like that, somebody might ask if they might just ask, do you know what Six Sigma is? So at least if you know and understand what it is, people know that you have this concept of continuous improvement and looking for trying to drive out all errors or any problems that you have. And here's the concept of Six Sigma. We looked earlier where most companies are looking for that three sigma, which means 99.74% it meets the standard. That's what most companies will look at and say that's acceptable. Most products, that's going to be acceptable. Customer standards, they're going to be okay with that. But the idea of Six Sigma is it goes on into saying out of 1 million products produced, 3.4 errors. So, which is almost no errors. And again, people don't really believe that they're going to hit that number, but it's the concept and idea of ever improving, always looking to get better. Again, just if you're not trying to improve, you're going to get left behind. I saw an article this morning. I knew Kmart had been struggling, but 20 years ago, actually a little more than 20 years ago, 25 years ago, they were pretty strong. And it says they're down to their last 4 stores in the U.S. So they're almost done. In 25 years, which is a relatively short period of time, they went from one of the leaders to almost gone. So again, got to keep improving, keep working on these improvements. This is a video on Six Sigma, much better than it is not statistical. And, there's some statistic in it, but it's definitely more interesting than the last video. Six Sigma, some companies are sending people off to be certified. You can be black belt and all this different stuff in Six Sigma, but at the very least, they'll talk about DMAIC, and at the very least, companies are using this process that is developed through Six Sigma to try to identify some of their problems. So let's watch a little bit about Six Sigma.
Imagine you've been tasked with a really important project. The company you're working for produces luxury cars. The production numbers are going down, and a lesser number of cars are getting manufactured each day. There also seems to be an issue with the quality of the windshield wipers that go on these cars. The question you are faced with: is there a way for the company to stop the stall in production and increase the production per day from 1,000 to 2,000? Also, is there a way to find out what's causing the drop in the wiper quality? There is. Six Sigma. Six Sigma gives you the tools and techniques to determine what's making the manufacturing process slow down, how you can eliminate the delays, improve the process, and fix further issues along the way. The concept was introduced in 1980 by Bill Smith while working for Motorola. Since then, Six Sigma has seen worldwide adoption. Six Sigma aims to reduce the time, effects, and variability experienced by processes in an organization. Thanks to Six Sigma, you can produce a defect-free product 99.9996% of the time, allowing only 3.4 errors per 1 million opportunities. Six Sigma also increases customer loyalty towards the brand, improves employee morale, leading to higher productivity. Six Sigma has 2 major methodologies, DMAIC and DMADV. Let's look at the first methodology. DMAIC is an acronym for Define, Measure, Analyze, Improve, and Control. Let's have a look at each of these stages individually and how it relates to your earlier problem.
Most of the time, people just say demand. They don't.
You determine what issues you're facing, what your opportunities for improvement are, and what the customer requires of you. Here, you look at the process as a whole and determine the issues with the manufacturing process. In this case, finding out why the cars have varying windshield wiper quality and how to optimize the current process to manufacture more cars. In the measure phase, you determine how the process is performing currently in its unaltered state. You determine the current number of cars that are manufactured in a day. In the current scenario, 1,000 cars are manufactured in a day. And each of these cars are outfitted with a pair of windshield wipers by one of 30 machines used. Some of the metrics measured are how many cars are produced in a day, time taken to assemble a car, how many windshield wipers were attached in a day, time that takes them to do so, defects detected from each machine on assembly completion, and so on. Following this, in the analyze phase, you determine what caused the defect or variation. On analyzing previous data, you find out that one of the machines that installed the windshield wiper was not performing as well as it was supposed to. Production was taking longer since the car chassis was being moved across the different locations slower, as cranes had to individually pick and drop the frame. This was because the wheels were attached to the car only in the last stage. Next, in the improve phase, you make changes to the manufacturing process and ensure the defects are addressed. You replace the faulty machines that installed the windshield wiper with another one. You also find a way to save time by attaching wheels on the frame in the initial stages of the manufacturing process, unlike how it was done earlier. Now the car can be moved across the assembly area faster. And finally, in the control phase, you make regular adjustments to control new processes and future performance. Based on the changes made, the company was able to reduce production time and manufacture about 2,000 cars a day with a higher quality of output. DMAIC is one of the most commonly used methodologies in the world. It focuses on improving the existing products of the organization. The second methodology is DMADV, which is short for Define, Measure, Analyze, Design, and Verify. It is used when the company has to create a new product or service from scratch. It is also called DFSS, or Design for Six Sigma. Let's take the scenario where the company decides to build a new model, a sports car. In the define phase, you define the requirements of the customer. Based on inputs from customers, historical data, industry research, you determine what you need to ensure your car becomes a success. The data collected indicates customers are drawn to cars which can achieve more than 150 miles per hour. Customers are also more inclined towards cars which have V6 engines and an aerodynamic frame. Then, in the measure phase, you use the customer's requirements to create a specification. This specification helps define the product in a measurable method, so that data can be collected and compared with specific requirements. Some of the major specifications that you focus on are the top speed, engine type, and type of frame. In the analyze phase, you analyze the product to determine whether there are better ways to achieve the desired results. Areas of improvement are determined and tested. Based on the analysis of the prototype created in this phase, you find that the product satisfies just about all of the customer requirements, except the top speed. So, research begins on an aluminum alloy that could possibly meet the speed requirements of the customer. Following this, the design phase, based on the learnings from the analysis phase, the new process or product is designed. Revisions are made to the model, and the car is manufactured with the new material. The analysis phase is repeated based on the new design. You also bring a focus group and see how they receive it. Based on their feedback, further changes are made. And finally, in the verify phase, you check whether the end result meets or exceeds customer requirements. Once you launch your brand new sports car, you collect customer feedback and incorporate it into future designs. And guess what? Your customers are loving the new design. And that is DMADV for you. Six Sigma has also found success in a number of different industries. The petrochemical, healthcare, banking, government, and software are some of the industries that have utilized the concepts of Six Sigma to achieve their business goals. Another commonly used methodology adopted by companies around the world is Lean. Lean is a methodology that aims to remove any part of the process that does not bring value to the customer. It means doing more with less while doing it better. The philosophy behind Lean comes from the Japanese manufacturing industry by Bob Hartman, who at the time was part of Toyota. Since then, across the world, services and manufacturing organizations have incorporated Lean within their businesses. But what if you could have the best of both worlds? A combination of both Six Sigma and Lean. That's Lean Six Sigma. Before we get into Lean Six Sigma, we've got a technology is used by companies
We're going to
that
stop
you
there. Lean Six Sigma that they talked about there at the end, you know, the lean is a process of just pulling out anything that isn't adding value. So they put that with Six Sigma and those concepts together and really just work to see how they can make the process as good as they possibly can. The interesting thing to me about this is really these 5 steps are just common sense. I mean, you know, if you're looking for looking at a problem and improving the problem, you look at these and go, well, of course that's how you'd want to do that. The funny thing about it is that people don't do it. You know, they just want to jump into whatever the problem is, and I've got an idea to fix it. Let's try to fix it. You know, that seems to be the majority of the way people solve problems. Let's just try something and see what happens. Um, but using this process, you can get your results faster. They can be implemented easier. You can have some statistical results to be able to show, particularly upper management, why you should make these different changes in the process and figure out what's going on. So, and it was a little bit later in my career where I really started trying to use these exactly how they were meant to be used, and I found that it worked really well. So and they went through some of these, but defining, you got to know what your problem is and what you're really looking for. Sometimes people, they don't even know exactly what they're really trying to do. They just kind of addressing something. So measure current process. You got to have some sort of measurement to see where you're at, because when you get down to trying to figure out if what you're doing is helping, you've got to have some measurement to see if it's really it really is. Analyze, you're looking at the root cause. And that's another thing that I think people miss. They find a problem, they want to say, okay, that's the problem, and move on. But what you really want to do is keep digging until you find exactly what the root of the problem is. Because it's just going to come back if you don't fix that root. Improve the process. So, looking at the root problem, how are you going to fix that root problem? And then control it. Takes time a lot of times to really turn things around. So when you find that root cause, it takes a little time to figure out what you're going to do, and then sometimes the effects of fixing that root cause come later down the line. So there's some patience there, and that's why you got to have control on the process. A byproduct of not finding the root causes, you get a quick fix return, and then people combined with people not controlling the process, you end up exactly back in the same place you were. I've seen it happen dozens of times. It used to drive me crazy. You know, they would fix something, think they fixed it, wouldn't control it. Next thing you know, a year later, they're looking at the same problems over and over again. So using this is a very good way to approach it with Six Sigma. Acceptance sampling, you know, you have sampling that can be used, particularly in manufacturing. They're going to look at the batch. Most top manufacturers, they're going to have a batch that goes through. They're all going to be set and marked essentially as being this part of the group. And then they're going to take samples from that group, decide whether it's going to be good or not. So that's acceptance sampling. There's different plans and different ways that they can do it. You can do it at different points. Most organizations will try to have it at different points along the line, because if you don't catch it early in a batch, you might produce an entire batch that is bad. Um, didn't happen too often, but sometimes we would run into issues where, you know, a mask error or whatever it might have been, something went wrong in the process, and we would throw away thousands and thousands of them because they weren't good. Uh, More often, companies are trying to do it down the line. We saw that in that flex line video, at least with the how much it was filling the bottle. They would check them, you know, in line to make sure that they were all right. That was usually one of the bigger problems that they had. So doing that. Decisions for managers. So you've got this, particularly on these first couple, when you were looking at samplings and trying to identify quality issues, um, the cost of the product and the volume. So, what are you really trying to do? Are you trying to have a super duper high quality product, or are some variations okay? Is your process stable? Is it something you can expect higher quality? Sometimes it's better to just run through your product and test them and pull out the ones that are bad. Maybe it's not stable enough. Lot sizes, looking at the lot size, if you've got to go back and redo a lot or throw away a lot, it's important. Where you're going to check it, it's important to check your inbound materials too, your raw materials, to make sure that they're correct. Um, we used to get a lot of our cards printed off-site, so what we would blister those products to, and every once in a while, somebody wouldn't check the cards and there would be something wrong with it. It would say something wrong or be the wrong product. Or one time we had some totally different phone number on there, and just weird things can happen. So your inbound materials you need to look at, your work in progress, your WIP, as it's going through the process, you'll want to check it. And then this mentions prior to costly processing. So you might have a point where if it gets past point X, whatever it is, it's going to be really expensive. So you might want to check right before that. We look at the goal. We're going to see that sometimes they move their quality process around. Which tools to use? You've got all kinds of different tools to use. I would recommend using spreadsheets and statistics as often as you can. Service. Sometimes it's pretty tough to put statistics with a service. Um, it's hard to quantify a lot of parts of it. If it's a lawn service, is your yard mowed right? It kind of depends on the customer if it's mowed right or how you want it. So for a long time, it was kind of like that idea of, well, we can't really measure it, so we're not going to. Goes back to this idea of try to find some way to. More often, service companies are finding statistical ways to measure things. Sometimes they aren't very objective. It might be just strictly off a survey. For instance, what's something that if you were to do a survey and give a service feedback, that you might have a completely different view from somebody else? Can you think of something? Think about a restaurant. How could your view be completely different from someone else? You might say it's wonderful, somebody else might say it's terrible. Any ideas? I can tell you, for me, I hate black olives. I hate them. Cannot stand them. If you gave me food with black olives in it, I'm probably not going to give you a very good review. However, one of my kids used to, when he was little, he used to put them on his fingers and eat them. He likes them. I couldn't stand them. I can't stand them. I hate them. So you might not like a certain kind of food. It might have been prepared perfectly, but you just don't like it. So that's one thing that makes measuring services very subjective. It depends on the preferences of people. But you can look at certain things like at this hotel, um, checking in on time, number of complaints received at restaurants, number of times the telephone rings. Um, it might not be able to capture everything to meet that service, but the thought is if you are measuring these things and paying attention to them, you're starting to build a culture of quality in your business. So the other things that may be a little more subjective, you're still trying to meet those and improve those and make them work the way that they should. So services can be tough, but people are finding ways, and more and more it goes back to how they can establish a culture of quality. Across the organization, statistical control, quality control needs to be used to be able to measure all sorts of different things. Marketing needs to think about it, what the customer wants. How are we going to be able to meet the standard that the customer wants to create more sales? That front end side of it. Finance, if you're having problems with quality, they need to be able to see that and then put a financial number. We're getting X amount of returns and all this. They need to be able to put all that together. Human resources, if you don't have the people who can do the job, particularly in service industries, you've got to be able to look at that and know if you're doing what you need to do and having the right workers. IS, they are providing this to people. So most of the time what will happen is if you want to find out some of this information, you go to IS and get the data, and then you have to process it. That's why we're doing it in this class. Usually, they don't want to process it for you, so you're going to have to do it. But they'll get the information to you or find ways to make it readily accessible. Lots of times, they could, if I knew something that I wanted regularly, they could put it in our system where it would generate a report for me regularly, or I could request a report. I always thought they were being super helpful until I realized that really it just means they're creating a way for me not to bug them. So, they're going to do those things to help. That is actually the end, but I think what I'm going to do is just go ahead and I'll run up and run through these problems because I don't think I can get through much of them in 10 minutes. So I'll go up and I'll create a video of me going through examples of these problems, and then I'll post it for y'all to look at. And we'll just end here for today. Work? All right, you guys have a good rest of the day. If you have any questions on the problems, feel free to just come by and ask.